Let's talk about catalysis today. A catalyst is a chemical species that increases the rate of a reaction without itself being consumed, and it does that by modifying the reaction energy profile for a particular process. So if we consider the reaction coordinate diagram that I've got drawn down below here, we see that this is an endothermic process because for this reaction, the change in energy is a positive value, so we know that it's an endothermic process, and it certainly has a nice activation energy barrier. And so we know that in order for a reaction to occur, according to collision theory, you need to have collisions. Those collisions need to happen with the proper orientation, and that each collision that's going to occur has to have greater than or equal to that minimum activation energy. So what a catalyst does is it provides a pathway that has a lower activation energy. And because this new catalyzed pathway has a lower activation energy, more collisions will have the necessary energy and be effective, thus the reaction rate will increase. So it's important to know a couple things about the way a catalyst works. It lowers the activation energy, but it doesn't change what the difference in energy from the reactants to products is. That's about what you have. And so it's not going to change delta E. It's also important to note that when you lower the activation energy by changing the pathway, you lower the activation energy for both the forward and the reverse reaction. And so it does not affect your equilibrium constant. So there are three different types of catalysis we're going to talk about in a little more detail. The first is heterogeneous catalysis. And so as the name implies, we have two different states for the catalyst and the reactant in this case. So most commonly, this is a solid metal catalyst and then either a gas or an aqueous set of reactants. And heterogeneous catalysis typically happens or can be envisioned as happening in four different steps. And so the first thing that happens is that the reactants are adsorbed to the surface of your metal catalyst. And so adsorption just means that they collect on the surface, and so there's a chemical interaction between the reactants and that metal surface. And that tends to activate the reactants in that often, at least for a number of the different processes they've identified, what's happening is as the electron density flows in order to form that bond or that adsorption with the surface, you're weakening the bonds within the reactant, which makes them easier to break as the reaction proceeds. Once the reactants are adsorbed onto the surface, they are going to be able to migrate around the surface, and this allows them to come into contact with the other reactant molecules necessary for the reaction to occur. The third step is that the reaction actually happens, and then the fourth step is when those the new product molecules, escape. So let's add some visuals to this so it makes a little more sense in terms of what it is I'm talking about here. So if we imagine our metal surface, initially we have some reactants that are present, and the first thing that's going to happen is that they are going to come down to this metal surface and they're going to be adsorbed on the metal surface. Once they've been adsorbed on the surface, they're going to be able to migrate throughout the surface in order to come into contact with one another. And so once they come into contact, then they're going to be able to actually interact, because just like we had before, collision theory hasn't fundamentally changed. In order for molecules to react with one another, they have to collide. They have to come into contact with one another. So here is my collision where these particles are now able to interact with one another. And so they're going to react. And that leaves us with our product molecule bound to the surface. And now that that product molecule is bound to the surface, it is going to escape from the catalytic surface and go off as a final reactant, as a final product. The second type of catalysis we're going to talk about is homogeneous catalysis. And in this case, the catalyst and the reactant have the same state. So a solid example of this that we'll do in class is taking hydrogen peroxide, which is an aqueous solution, and this will decompose to form water and oxygen gas. And typically this process is quite slow. However, if you add a catalyst, so in one possible catalyst is an iodide ion, coming from aqueous potassium iodide, you're going to dramatically increase the rate of that reaction. And since catalysts aren't really reactants and aren't really products, since they're not consumed, we're going to write them over the arrow of our overall reaction to indicate that they're important to make the reaction happen. They're definitely there, but they're neither reactants nor products. So the last type of catalysis that we're going to talk about are enzymes, and these are biological catalysts. So enzymes are protein molecules, so chains of amino acids, whose function is to dramatically increase the rate of the chemical reactions that happen within your body. And that's important because most of the chemical reactions you need to survive wouldn't happen fast enough at physiological temperatures for you to exist. And so our enzymes actually are able to increase the rate of the chemical reactions they catalyze by 10 to the 6th to 10 to the 18th times faster than they would normally be. So the increase in rate is dramatic compared to what they would be. It's also noteworthy that enzymes are very specific. So each enzyme is only going to catalyze a particular reaction. And so that allows for fine control within your body as to the different rates of various reactions. So they're highly specific. And I just want to give you one example of an enzyme we'll talk about more in class. But carbonic anhydrase is an incredibly important enzyme. It's responsible for maintaining the buffer system and the relative amounts of carbon dioxide, bicarbonate, and carbonic acid that form the buffer system for your blood, that carbonate buffer system. And the reactions that it is catalyzing are as follows. So not only is it maintaining that blood pH, but it's able to, in this process, remove excess CO2 from your tissues. And carbonic anhydrase is interesting in that it is one of the just absolute fastest enzymes in your body, and so it's able to catalyze 10 to the 4th to 10 to the 6th reactions per second. So we're not just talking about how much faster it would have been than without the catalyst. We're just talking about 10,000 reactions per second for every one enzyme. Let's take a quick closer look at this carbonic anhydrase enzyme. Enzymes themselves, like I said, are proteins. So they're made of many, many amino acids. And so if you look at this image, you can see all the many atoms that go into making this really gigantic molecule. But with an enzyme, typically there's only a small region of the enzyme that actually is directly involved in the catalyst process. It's all necessary for it to function, but only a small area is actually involved. And so in this case, the active site has been identified as 3 histidine residues. So that's a 5-membered carbon and nitrogen ring, and then a zinc ion. And so out of this whole molecule, the active site is this small region where the reagents are able to interact with the enzyme and speed up the process. It's also worth noting that enzymes are inspiration for the catalysts we'd like to be able to use outside of biological systems. So this particular image is taken from a news release from the Lawrence Livermore National Laboratory, where they're using carbonic anhydrase as a starting point for designing catalysts to use in carbon capture technology. So cleaning emissions and those sorts of things and pulling the CO2 out of those emissions and trying to reduce that environmental impact. So if you're interested, I've got a link down here at the bottom that you can go and check out how carbonic anhydrase, how this biological catalyst is serving as the inspiration for catalysts in other realms of our world.